Before you this video, make sure you've read through this question and you have a good understanding of what you're being asked to accomplish here. This example is a matched pairs t-test. And in section 9.3, you wrote this if you read the chapter, and they talked about how you had to look at the difference between, in this situation, a before exercise program, after exercise program. So if you notice here, I have these results that are paired by individual. So the first experimental unit was at 99, and then after was at 97. And this is in kilograms. The next one was 57, and then after 3 weeks at 55. I took all these before and afters and I subtracted them. Now it's important that you realize that we are going to use the difference. My focus is on the difference, the average weight loss between the start of the program and after the 3 weeks on the program. So this data is the data I'm going to use. Right, so if we are assessing whether we have support that the exercise program is effective in reducing weight, then our parameter of interest is the average difference between weights before and after the exercise program. It's important that we state that. You have to say what the parameter is. It's the average difference before minus after. Then the next thing you need to do is write your null hypothesis. Remember, your null hypothesis is saying there's no change. So if there's no change, the before and the after, we would expect the average difference to be at 0. If there's no change in weight, the average difference is 0. We're testing the claim that there is a difference, and in fact, that difference is going to be greater than 0, that there should be a positive difference. Again, go back to the context of the problem. A positive difference is saying that people are losing weight after the 3 weeks. This person dropped from 99 kilograms to 97. That's a positive difference of 2 kilograms. So my HA is my mean difference is going to be above 0, greater than 0. And we were also told that our significance level should be 5%. Next, we have to take our data and analyze it. Now, how you do this is you put the data in your calculator. You go to Stat, Edit, and you enter the data into List 1. And then we need to stat calculate our stats from List 1. If you need to pause the video so you can enter this so you can follow along, please do. So I now know that my mean difference, my average difference of this sample is 2.5 repeating, or 2.56. And that the standard deviation of my sample, so I'm using S of X, the standard deviation of this sample is 1.81, and my sample size was 9 people in the exercise program. So now I have my data from my sample, and that's going to be important for the rest of our calculations. Before we can actually calculate anything, we need to make our checks and assumptions. So the first thing we're going to look at is independence. It's a random sample, and our sample size of 9 is less than 10% of all people in the program. I think that's a pretty safe assumption, although I don't know how many people total are in the program. And then there's one extra thing that you have to add with matched pairs. This is new. This is different than any other. You have to include a sentence of how the 2 columns are linked. How is it that we're getting this paired data? The data is paired before and after for each person. You have to state that in there, that the before and the after is the same person, the same experimental unit. Once we've done that, we can move on to see if we have normality. It's not large, okay, so we cannot use the central limit theorem here. However, by looking at the sample data, it is nearly normal. So once again, remember I have this sample data in my list 1. So I'm going to go into my stat plot here. There were 3 things to check to see if your sample was nearly normal. The first is a histogram. So I'm going to press zoom 9. I'm going to zoom in my statistics. Overall, I see this is fairly normal. I don't see any skewness. I don't see any outliers. But I continue by checking the box plot with outliers. So I check the box plot, zoom 9 with outliers. Again, I don't really see any sharp skewness. It is a little bit longer on the left side, but I don't have any outliers. One more test to just secure that it's nearly normal, because that box plot was looking a little bit more skewed than the histogram was. We can check the normal probability plot, which is the very last one right here. We're going to zoom 9. And this should be fairly linear. And overall, I can see that this data is fairly linear. Nothing's really deviating from that linear path. So I note that based on the histogram, the box plot, and the normal probability plot, by looking at all 3 of those things, that the sample data is nearly normal. It's nearly normal. It's not skewed. There are no outliers. With conditions met, we'll conduct a matched pairs t-test with 5% significance. At this point, I want you to try to carry out the calculations on the back. Pause the video and then resume when you have a p-value calculator. For those of us who have calculated our p-value, let's go ahead and re-examine what we know. Mu is 0. Our degrees of freedom is n minus 1 equals 8. And guys, this is the first time we've mentioned this. We just said we were going to do a t-test that is with 8 degrees of freedom, and you have to mention that on an FRQ. If you're working with a t-test, you have to mention the degrees of freedom. Our sample data gave us a mean of 2.56. Our sample standard deviation is 1.81. And then our standard error for our sampling distribution is going to be 1.81 divided by the square root of n. From here, we're going to calculate our test statistic, which is a t. Remember, we're working with a t-test. So what I can do is I can take all that information and put it into this formula. Statistic, 2.56, that's from our sample, minus the mean, which we believe to be 0 if there's no difference. That's the claim we made in the null hypothesis. Divided by our standard error, which is going to be this 1.81 divided by the square root of 9. And this gives us a test statistic of about 4.239. That is our t-test statistic, 4.239. Well, think about our distribution. If this is centered at 0, we said our mean was 0, and I go out to 4.239, that is beyond 3 standard deviations from our mean. If I go 1, add 2, add 3 of these standard deviations, these standard that value, 3 standard deviations is 1.809. My test statistic here of 4.239 is even further on that curve. I can't even draw it on there. It's not even on the curve. Already, I'm starting to see that this is pretty unlikely. This is so far off down on this tail. This must have a very low p-value. So we need to calculate this p-value. Remember, p-value is a conditional probability. The probability of our sample difference given the average distance difference is actually 0, given that our data is centered around this 0. So we can get this value either in our table or using our calculator, looking at the probability that t is greater than 4.239. I'm going to show you in the calculator just to remind you that if you go to stat second VARs, we're going to be doing TCDF. My lower bound is 4.239. My upper bound is infinity. My degrees of freedom is 9 minus 1, which is 8. And I get a very small p-value of 0.0014. So about 1.1%. So about a 0.1% of obtaining a sample if the mean difference is actually 0. So what does that mean in context? Pause the video and think about your conclusion and then restart the video. Because our p-value is less than alpha, we will reject the null hypothesis. Our p-value was 0.0014, which is less than 0.05. If the p-value is low, reject the H of O. You reject the null hypothesis. So let's think about what that means in context. Okay? So in context, we can conclude that on average, people lost weight after 3 weeks on the program. That is saying that we reject the null hypothesis, that they are not losing weight. Remember what the null hypothesis said, that the mean difference was going to be 0. We have enough evidence to say that no, people are losing weight on average after 3 weeks on this program.